Hello everyone, at present basically we are in the module number 4 on VLSI testing. So in the last lecture basically we were talking about optimization of the test patterns, that is ATPG algorithms, how we can develop or generate good quality test patterns which are optimized with certain parameters. Like for some case how ATPGs or test patterns can be generated for very large circuits, that is one way of optimization. Other ways of optimization, as we were looking in the last lecture, that how we can develop good quality test patterns, such as one test pattern can test stacked faults as well as more advanced faults like delay faults, bridging faults, end detect faults, etc. So basically we will now today also we will continue in this direction, where we will be finding out how we can develop more optimized test patterns by compressing them. As we will go, we will detail out more on that. So basically we can see that how test patterns can be optimized. One way is that you can have a very good algorithm to find out the test patterns. That is how we can handle large scale or complex circuits. Second is how we can generate good quality test patterns. What do you mean by good quality test patterns? Test patterns which can detect multiple faults, which can detect faults of advanced types, apart from stacked faults like bridging, delay, end detect, etc. So basically last lecture was mainly focused on that, where we have seen how to generate test patterns which can detect stacked as well as bridging as well as delay, and there can be certain other important fault models which can be detected. But the main goal is that how we can develop test patterns so that it can handle multiple faults. The first topic is basically how we can go for large, how we can generate good, advanced or make the ATPG algorithms intelligent so that we can detect faults in a much faster manner. So that by that way you can find out better paths where we can sensitize the fault, better path by which we can propagate the faults, so that whatever values you require can be justified. So there are a lot of heuristics based on that. We have not emphasized much on that because that is actually mainly applied when the circuit size are small. Otherwise, this is a part of traditional VLSI design, so VLSI testing courses. So you can take off any textbook or any material on CAD, you will find out lot of heuristics which tell you how to find out good paths for fault propagation, sensitization and justification, so that you get good quality faults in the way that they generate the test patterns faster. Next important part basically which you are going to see is something called how can I compact the test patterns, because you may have lot of test patterns, but one important thing you have to observe that 90% of the values of Boolean variables which are obtained after running an ATPG algorithm are X. I will give you a simple example. AND gate, you want to detect a stacked 1 fault, say. So stacked 1 fault, that means you have to have a 0 over here. How we can get 0? You can have 0 0, 0 1 or 1 0. These are the 3 patterns which I can find out to detect this fault. But I can simply write it in this fashion, that I can have, to detect a stacked 1 fault, I can have X 0. That is, this value can be anything, I just need to set one value as 0 and I can detect the faults. So if you take a large or a general circuit practical example, such X's in the test pattern means which can be either 0 or 1 occupy more than 90% of the variables. That is very, very interesting observation people have found out. Now using those X's, can we compact the test pattern? So if the input bit width is say 100 and there are a lot of don't care variables, how can we compact the test pattern? So in that case what is going to happen? It will be optimized in the sense that you have to have you can apply a less bit width patterns by a tester, so that you can save on the tester part. We will detail out by examples. So that is the idea of test compaction or ATPG optimization, that instead of having very wide test patterns, can we make it smaller in width. So smaller in width means less number of channels from the AT, etc. Another level is, which I have told you, that can we do automatic test pattern at a higher level of abstraction, which we will see further down the series in this module. But today we will be concentrating on how we can optimize test pattern by compressing them. We should take an example. So for example, let this be a circuit. There are some input pins. So there are say n scan chains, or I can tell you that n input pins, because scan chains has to be loaded. So if there are n scan chains or n inputs, so n patterns parallel you can load. And an AT is called an automatic test equipment. It has say m channels. Generally it happens that m is always smaller than n, because the circuit may have 1 0 2 8 2 4 pins or more number of inputs, higher number of inputs like 100 inputs, 200 inputs may be there to test a circuit. Generally why we call m is less than n, basically n is the number of parallel channels from which you can apply patterns to a circuit, and aim basically and aim is the ATE channels. ATE can have lot of channels, but you have to pay. So for every channel you use and the speed you use, you have to pay, because ATE services are given by vendors. So ATE may have some 200, 300 channels, but more number of channels you use, more amount of money you have to pay to the vendor. So what we always try to do is that we have to optimize in such a fact that our test width is less. Maybe by 10 patterns, 20 patterns you will be able to do, because more test patterns you want to apply in the sense is maybe 1, 1, 1, 1, then next pattern is 1, 0, 1, 1. So 3 patterns are there. So more number of patterns means more time you will be using the ATE. So more amount of money you have to pay. And also if you use more number of channels, of course the price will rise. So what we always try to do, compact the number of test patterns as well as compact from this side. This one if you use less number of test patterns, generally you may lose on coverage. But generally we have already discussed in the previous lectures that there are a lot of faults which are equivalent, and basically stacked, one of the beauty of stacked faults is that due to fault dominance and equivalence, the number of stacked faults or number of patterns are not too large even for a very large circuit. That means basically the number of patterns to be applied like 110, 101, some patterns are there. This is generally not too large, or in other words, I should not say that it is not too large. In other words, if you try to optimize, if you reduce the number of test patterns in that fashion, basically you are going to lose on coverage, because ATPG algorithms will always try to give you the minimum amount of test patterns required to cover all the faults. Say for example, I have 100 faults. ATPG algorithm will give you some 20 patterns or 10 patterns which will be able to cover all the faults, and there are algorithms which will give you the minimal amount of factors to do that. If you further reduce it, you may lose on coverage. So generally, compaction on this manner or reducing the number of test patterns is a different problem than test compression which you are trying to do today. So reducing the number of test pattern means basically you have to find out the minimal set which can cover all the faults modeled. So that actually comes under automatic test pattern generation and is a well studied area. But now today we are saying about compaction. For example, if you have 1 0 1 0 and say all other are x x x x, not required to be anything. So what I can do is that I can put some arbitrary circuit inside which will generate these arbitrary values, because I do not require to purchase ATE channels for that, only I use these deterministic values from the automatic test equipment. So these are some arbitrary values, I can just put zeros and ones, I do not require to put channels. That is the basic idea of a test pattern based compression. So the idea is that number of channels and memory depth. So what is memory depth? Memory depth means how many test patterns you are applying. This directly falls under that. So more number of test patterns, more number of depth, and number of channels. As I told you, more number of channel means you have more number of pins required, more number of parallel loading you can do, but that will actually pay the cost. So memory means what are the number of bits you are using. So if you the more number of bits, more number of patterns and more number of bits per pattern will increase the memory. So for memory in the ATE you have to pay. But memory is not that expensive, because nowadays memories are cheaper. More important is how many physical channels you are occupying. So that if you are using 10, the other 10 can be used by other vendor, the other 20 can be used by some other company, so you have to pay less. So memory is a constraint, but we are more interested in the reducing the number of channels. So basically what we are trying to do, we will be doing, basically even if n is there, we will try to limit m as less as possible. But still we want to apply all the test patterns. But what we leverage out, they do not care bits in the automatic test patterns generated or the patterns which are generated. So in gist what we are trying to do, 100 input lines of the circuit, maybe 80 lines will be don't cares, only 20 lines we have to give justified exact values for applying the test pattern. So how can we find out that 20 and what we have to apply in that 20, so that you use, instead of 100 pins from the ATE, you use only 20 pins from the ATE. So that is basically we are trying to do in this. Because I told you, reducing the number of test patterns falls under ATPG generation, and in fact ATPG algorithms are well optimized so that they do not generate redundant kind of test vectors, they generate the mostly minimal amount of test patterns required to test all the faults. Again describing pictorially. So basically this is your ATPG algorithm which will generate the tested stimulus, that is minimum amount of test patterns required to detect the faults. But it will have 0, 1, 0, x, 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 x. ATPG is not binding the number of bits. What is the input number of channels for the scan chain, or what are the inputs of the chip to be tested, that is the width. So that is the input pins of cut. That is circuit under test. So that many pins it will, that many width will be the of the vector it will generate. So that is really done by the ATPG. Because already I discussed, so that if you are having a stuck at 0 fault, so stuck at 1 fault over in the AND gate, you will generate x0 or something, but this bit size will be 2. ATPG is designed to generate these vectors for all the input pins of the circuit under test. So now basically let us see what we are trying to do over here. So this is your ATPG algorithm, it is generating some state stimulus. Now this is the ATE memory. So what you can do, basically some part of the ATE memory, some patterns we can directly put into the memory, and some patterns which can be compressed, because I told you if you have a pattern where there is no excess, no don't care, that has to be directly put into the memory. But for most of the patterns, 99.9% of the vectors can be compressed. So compressed means I will reduce in the width and I will put it into the ATE memory. So now you can see basically this width may be equal to n, this width may be equal to n, because n number of width is there, but then it will be compressed, now it will be actually equal to n. So m is much smaller than n. So you are using less number of width of the ATE memory. But now this is again n, because practically you have to apply them to the test vectors, to the card circuit under test. So there is a decompressor circuit in your chip which will take this compacted pattern, compressed pattern and apply it to the cut. So that this is a circuit you have to put in all your ICs. But it has been found out that now design cost is not very high. So this is also called design for testability. So you can have this extra compressor and decompressor circuits, and still if you reduce the number of pins of the AT, it's a profitable business. So it is slightly counterintuitive, but it's true basically that even if you have some extra circuitry but reduce on the pinouts of the AT required, reduce on the test time of the ATE, you are going to save on money. And the output is something called a compactor, because of course the output can also be Z, X, huge number of outputs can also be there, but again we are not going to take all the compacted response, all the direct responses from the cut and put in the AT memory and analyze. It will not be a very good idea, we will be going for a compaction. Basically a slight difference, compression is lossless, so when you are having a test vector, we will compress in such a manner, so when you decompress it, exact value you will get, you will have no loss in information, but compaction means it is a lossy. So that means if the output vectors we will compress, we will call compaction. So the output response will be compacted, we will give you by examples, and then we will feed it to the AT memory, but in this case it will be a lossy compaction, so sometimes there will be aliasing. So aliasing means the fault is there, but because of this compaction you may think that it is normal. But there are a lot of techniques, still we can reduce the width of the output response and the aliasings are not very high. So we will now go into that. So it has been found out by ITRS data in 2013 that by 2020 1000x compression will be required. That means circuits will be so large in NOCs and SOCs, but with the increase in size of the circuit, the input pins will also rise, or the input channels will also rise. I should not call it basically input pins, basically in this they are actually scan chains or scan inputs as well as your basically normal combinational inputs where we can apply the test patterns, they will also rise. But with the rise in the circuit size, it is very interesting that the number of excess or don't cares in the test patterns will also rise. So there will be 1000x compression will be needed by 2020, or it will be possible, because otherwise the AT cost will become too high and it will not be a profitable business. But again, if you are compressing, then of course you have a decompressor and a compactor inside a circuit, but as I told you, it is very counterintuitive, but it is true that even with this extra DFT circuitry, but reducing the ATE time and ATE memory, you are making a profitable business. That is the motivation. So there are two types of compression, one is called dynamic compression, one is called static compression. So dynamic compression means you have to trigger, it is a part of the test generation program embedded in the algorithm. So in this case you have to motivate or modify ATPG algorithm so that you have more excess, more don't cares, and also in a very compatible manner, as I will give you by example. Or in that case you have to, in other words, in a layman's language, you have to direct your ATPG algorithms to generate test vectors which are more compressible. So this is basically called dynamic test program generation, but not very popular because of the idea that if you just use, because our ATPG algorithms also has to be faster, because you spend too much time on generating the test patterns and then compressing is not a good idea. And the beauty, as I told you, that if you take a very large circuit also, and also take a general ATPG algorithm, the number of don't cares are very, very high. So in that case, you do not itself require to tweak the ATPG algorithm to generate circuits with or test patterns with more number of X's, not required. They themselves are basically there. So therefore dynamic test compression is not very popular. Basically people go for static compression. So static compression means you have normal ATPG algorithm, do not alter this, whatever you get, you will have anyway you will have get lot of excess you will have in these vectors, you use them to compress it. That is called actually post generation phase. We generally go by that. Now there is something called vector compatibility, that is very very important to understand the compression. So you have zeros, ones and something called x, that is don't care, it can be anything. So if you see two vectors are there, if both of them are 0 0, it's compatible. Okay, and if you have x anywhere and it may be 0 or 1, anything it is compatible, 1 1 and compatible, 0 1 and 1 0 they are actually non-compatible, very obvious. So if x means it can be anything, so you can see that 0 0 is a comma, 0 0 you can put 0, 0 1 non-compatible hyphen, 0 x you can put it 0, so compatible business, 1 0 non-compatible, 1 1 will be 1, 1 x will be 1, these are all compatible. Similarly, x can be compatible with everything. So compatible bits can be merged, very obvious. Example, there are two vectors test patterns which are generated. So you can see that they are compatible because you can just see that 1 1 0 1, see the 1 over here and it's a x over here. So it's a compatible set. And non-compatible is here because in this position this is a 1 and this is a 0. So these two vectors cannot be merged, basically non-compatible. Now basically there are some ideas I will tell you. Say for example, these are the test patterns which has been generated. Let me just along for you. So there are some test patterns which is generated and somebody has sequenced them. Now you can see, you can easily see that 2 and 3 are compatible because 1 1 0 x x x 1 1 0 0 1 1 0 x. So basically this is compatible with this. So you can retain 2 and merge 3. That is what they have done. So it is 2 3 I have compacted in this manner. You can observe the second bit. So it is 0 and it is x, so it will be retained as 0. So you can see that it is retained as 0. Now 2 3 and you can also see that 2 3 and 5, 2 3 and 4 there is a compatibility again. 1 1 0 x x 1 1 x is a very compatible vector. So your compaction will be 1 0, this one will go over here 1 1 0 1 1 0. So basically we have a compaction like this. Similarly you can keep on going about it. Now there are some important things. Here somebody has already organized it for me, is arranged in terms of 1 2 3 and 4 are compatible. You can see that there are a lot of x's that you are going to generate in ATPG algorithm. There is no problem about it. But somebody has to sequence them in proper manner so that you can find out the compatible vectors and reduce it. Now there are two things over here, as I was telling you, that basically there may be vectors like 0 1 0 1, sorry, these are this test vector 1, this is test vector 2, test vector 3. Sometimes we write in vertical fashion, sometimes we write in horizontal fashion. We write it in vertical fashion when you are saying that the inputs to the circuit, but because your circuit inputs are like this, right? So these are the circuit inputs like this. So in that case we write in a vertical fashion, but when otherwise also representing, we can write this in a horizontal fashion. You can observe there are a lot of x's, so you can make compatibility, but sometimes you have to reorganize the vector because nobody guarantees in ATPG that first this one will be generated, then this one, not like that. You can generate in any jumbled fashion. But to find compatibility, someone has arranged it in a very nice manner for me, so that I can get 2 3 and then I can get 4 and so forth. So, but in general cases there are a lot of heuristic, because if you want to try all combinations to find out the minimum number of test vectors by merging compatible vectors, you have an exponential problem, because you have to study all possible sequencing like 1 2 3 4 5 6 7, all possible combinations of the sequence, which is very very large. Then only we are able to find out the minimum number of vectors after combining them. But generally there are a lot of heuristics, in which case you do not actually go for all the possible orders. Basically you find out some of the best orders and try to find out a minimal set. But the idea here I have shown you that how vectors can be merged. So in this case ATPG will give you all. Then you can apply heuristics, find out some good ordering and then merge the compatible ones, and you can get a minimal set. Now in this minimal set basically you have eliminated some of the vectors, but there is no compromise in the basically in the what do I say, there is no compromise in the test coverage, because maybe I have reduced vector 2 3 4 I have merged, maybe 2 is detecting stacked fault at position 1, 3 is detecting some stacked fault at position something, and 4 is detected at some position something. Now if you merge it, basically you will find out that the same pattern will detect these 3 faults together. That can be found out basically. That 3 faults can be basically detected by this single pattern. So that is one way. Some people also put it inbuilt in the ATPG algorithm, and some people actually go by this reordering. So this is one way. As I tell you, you can say that this is a very good quality test vector because it can detect more number of faults. So detecting one pattern to detect more number of faults can be also obtained by compressing in that manner by vector compatibility. That is one way of doing it. But when I was saying that in the previous diagram, when I was saying that I do not want to basically reduce in this, then maybe 1, 2, 1, 1, 0, 1, some vectors are there. I do not want to reduce on this because it will lead to reduction in coverage. I was meaning that the vectors are non-compatible. So if you have some non-compatible vectors which are to be applied to a circuit to do that, if you cut on that, then there will be lot of problems. Like for example, if I want to merge these two vectors, or I cannot, if I eliminate this, there will be coverage loss. I was meaning by that. But then another way of finding good quality test pattern is merging by compatibility. We do this. But that is also a very simple one. Another important idea is that if you see in this case there are 2 x's, 3 x's, in this case there is a single x, in this case again 3 x's. So do I really require 1, 2, 3, 4, 5, 6, 7, 8? Do I really require 8 channels to do it? Or can I reduce the number of channels and have some inbuilt circuitry here in this cut? That is what I was saying, in this cut, that is I call decompressor. Can we reduce the width? Here they are actually I have counted. So we were having some 8 or 9 width. So do I really require that? Can, because there are a lot of x's, like here also there are 2 x's. Can I do it with 1, 2, 3, 4, 5, 6? Can I do it with 6 width rather than 9 width? Can I do that? That is very, very important. But for that, basically you will have a decompressor circuit here which will take the 6-bit patterns and generate the 9-bit patterns which is required. That is a more difficult problem to solve, and it will have a huge impact, because by this you are reducing the number of memory width of the ATE, but you are having the same number of channels. So if you are booking same number of channels for ATE, that actually pays a higher cost because you are taking more amount of hardware which is dedicated for your circuit. So that is why if I reduce this width, so it will be a better, more optimized solution for me in terms of cost effectiveness of the testing. So that is why I call test pattern compression by reducing the width. There are a lot of techniques, so we will discuss few of them today's lecture, few of them will do in the next lecture. First is the code based scheme. So coding theory is an entire subject by itself. There are millions of papers, textbooks which does coding. So there will be an input code, it will modify it, make it to an output code. So input code may be larger width, the output code will be a shorter width, there can be encryption. So many things come in the coding theory. Coding theory means you will have one shot of input, they will be encoded to other form. So that, but there has to be some means to recover back the input. Input code encoded, that is the coding, and there should be a method to retract back the old input from which you are generating the output. So you know the n number of literatures, books, subjects are available in coding theory because the application is huge. Cryptography, fault tolerance in transmission, so everywhere there are codes, redundant codes, then you have parity codes, you have, then basically we have also on the CRC codes. They are all used in the communication to avoid errors in transmission or recover errors in transmission. Cryptography, as we know, for security. So code itself is a very, very huge area, and even most of the techniques can be applied for circuits, but as it's not a course, means if I want to elaborate everything on this, there should be a separate course basically on coding theory, and then we can only see how it can be applied for circuits. So rather what I will try to do, I will take the very most popular coding techniques and see how they can be applied. So that will give you an idea basically how code based scheme can be used for data compression. Then you can take any coding technique and you will be able to apply. Next one is slightly more interesting, which is called linear decompression based scheme. So basically we will be doing the compression based on some linear operations like linear feedback, shift register, XOR networks. Some small circuits we will have which will basically do the compression and decompression. One very important idea you have to understand that I cannot make this very large. If this, because I told you, as I have told you, because you will have the decompressor and the compactor inside circuit, profitable option rather than taking more ATE channels and ATE time, but of course it cannot be as big as the cart itself. So you have to make this as small as possible, the decompressor and compactor. So that also has to be kept in mind. So interesting point is that this linear decompression based schemes use LFSR or XOR networks. So I mean if you do not have the background on this, just study about linear feedback shift registers or linear combinational circuits in any textbook on digital testing, you will find out, or any textbook on digital design, you will find out that they are very interesting properties like LFSRs with primary polynomials. There are certain polynomials which when loaded into the LFSRs as seed, they will be generating all possible patterns or exhaustive pattern generators without using a counter. For example, if you want to design a circuit which will generate values from 0 to say FFFF, so you will be required a 16-bit counter. But for example, if you do not really want to have the sequence like 0, 1, 2, 3, 4 to FFFF hex, I do not require, but all the patterns I will require in any jumbled fashion. That is very, very important in testing. If you look at BIST, just go and revise BIST, you will be finding that it is very interesting that I require all the test patterns from 0, 0, 0, 0 to FFFF. But I do not require a pattern sequence, because in test patterns generally you can first detect stack at 1, then you can detect another stack at 1, and then the other place stack at 0. You do not really bother about the ordering. But generating a 16-bit counter depending on the bit is a more costly affair or in terms of hardware. But LFSRs are very interesting, that if you load with the proper polynomial, then you will be finding out that they are very simple circuit with flip flops and simple 1 or 2 XOR gates, nothing more than that, much lower circuitry size than a counter, but still it will generate all the patterns from 0, it does not generate 0 basically, but from 1s to FFFF, or in fact the exhaustive state space they will generate, but the circuit size will be very, very small. So that is what is the idea. So you can go and revise, but for the time being just understand that LFSRs or XOR networks or linear networks are such circuits which can generate large set of patterns, and the circuit size is much smaller compared to their counter simple digital combinational implementation like a counter or basically a simple decoder. The circuit will be very, very large, but in that case with small circuit you can generate that huge set of test patterns, but the sequencing may not be updated. So basically that is why this linear decompression based schemes will do the compression decompression for you, but in fact the circuit size will be very small. There is something called also called broadcast scan based scheme. So broadcasting same values to multiple scan chain. So can we reorient the scan values or something so that same values can be put in multiple scan chains, so that can be done in parallel. So if 2 scan chains have the same value to be pumped in, so then what can I do? I can use the same channel of the ATE to do that. But again, this I will not discuss in today's lecture, that will be postponed to next lecture when we will be talking about optimization in terms of design for testability. Scan is one of the most important part of design for testability, so we will postpone it to the next class. But today we will be mainly looking at this. First, I will tell you about a code based scheme. Huffman code we always know. Here the width of the code basically depends on the frequency. If some patterns are of higher frequency, then basically your code width will be less. If some patterns are of more rare, then your encoding will be larger. The idea is that because some patterns say X is highly frequent, so you will be sending that multiple number of times, so you make the bit width less, so that you will require less channel width in memory or even in communication. Whatever you want to send many times, you will require less bandwidth or less number of pins to be sent. But whatever patterns are occurring more and more rarely, basically even if you have a larger bit size, bit width, there is not a problem, because you will be sending only few amount of time. So what I do, so this is an example of an ATPG sequence, so I partition it into fixed numbers. So I have organized into fixed 4 values, and then these are the patterns. I have found out that some symbol names I have given S0 to S6, we will find out that there are 4 bits taken together, so there can be 2 to the power 4, 16 patterns can be there, but in this test pattern basically only 7 are there. So this is the test patterns, and then we count the frequency like S0, which is equal to 0010, occurs 10 number of times. So these are the test patterns. I have made groups of 4, and then I am writing the symbol S0, S1 to S6. 7 patterns I have found. Like I have not found patterns like 1, 1, 1, 1. Doesn't matter. It depends on the test patterns generated, and then I count the frequency. Like S0 is 0010, the frequency is 10. S1 is 000100, the frequency 9 is so forth. So I have generated this. Now I will be encoding is a Huffman fashion. So you know that in this case we generate an Huffman tree, standard discrete algorithms or data structure algorithms course. So like S0, the number of we arrange it in terms of frequency, the algorithm is already well known, same Huffman tree algorithm. So you can find out that whatever is the higher frequency like S0, S1, they will be towards the root node, and whatever is having lower frequency like X6, X5, like these one are having lower frequencies, they will come to the lower levels of the tree. The encoding of this one is 1, 1, the encoding of S1 is 1, 0, S2 is 0, 0. So lower frequency will be down the line, so basically your bit width of the encoding will be larger. Symbols having higher frequencies will be towards the root, so the length of this will be less. So now you can see, if I want to again zoom it, so that way I am having this pattern. So for symbol pattern 0010, highly frequent is 11, next frequency is this is 10. So you can see these S0, S1 and S2 are highly frequent patterns, so the code word size is less. So that means in the ATPG this will be pumped more number of times. So in this case you will be only require 2 channels. But these are very rare occurring phenomena. So in this case you will be requiring 1, 2, 3, 4 and 5 channels. So in channels are basically also multiplexed. You can also multiplex the channels so that you can have more efficiency of the ATE equipment. So depending on requirement, patterns will be sent to your chip, requirement the same lines will send to the other chip for the other vendor, but they will be multiplexed. So in this you can see that we have more number of patterns, means if you are using all this, so everywhere you will be multiplying by 4. But here actually these are occurring more number of times, so only 2 pins of them are required. So that way we basically optimize. But again of course, it is very important that when I get this as 1 1, the decompressor circuit should generate inside this. So maybe 1 1 will go from the ATE, so I should write this in ATE. So ATE will generate 1 1, 2 pins will be there. I am using for the timing, and it will go to your cut. So cut will be getting 1 1. Inside there should be a circuit of decompressing it. It will be generating it as 0 0 1 0. So there is a decoding circuitry should be there for the Hoffman codes, which is a very standard circuit you can study from any textbook. So in this case also 1 0 and 1 0 1 will be there. You will be able to generate this code, but the output from this decompressor will be exactly this pattern, because this is the pattern what has to be applied to the cut under consideration. So as I have told that there is a way of generating the inputs from the output words. So you have to generate a circuit for that, and you will be able to do it. So idea is that, so now people have found out that if you try to compress everything and send, then your decompressor circuit can be very large. So they have thought of, there are a lot of, actually I told you that this is the base scheme. Now a lot of offshoots has been found out, like there can be another coding scheme called dictionary, there is some other coding scheme called run length coding. So there are different coding schemes, hundreds of coding schemes are available. People take them, apply the base, and they do a lot of modifications on them. I am going to give you an example on what modification people have thought. People might think that there are so many patterns which are low frequency, very less they occur, but still if you are using this for encoding, then your decompressor circuit may be large. So one option is that I will take only the most frequent code words and I'll encrypt them, or I will code them using the whatever, like in this case Huffman code, and others I will directly pass, so that my decompressor circuit is not that large in size, or does not take more area, because only for the rare occurring patterns you require more width basically, for others you do not require that much width of the ATE. So let once in a blue moon one pattern is applying, for that I will take all the channels of the ATE rather than making the decompressor circuit too large. So they call it basically selective Huffman based coding. So in this case there is something interesting. So you have to have one LSB, which one will be telling whether the code is, whether it is encoded or not. Like as I told you, they are highly frequent, the first 3 bits are highly frequent. So they are highly frequent, so you can see that the MSBs are 1. So that means these are the 3 stuff which you have to decode or decompress. But in the last one you can see all these MSBs are basically 0. That means they are non-compressed codes and they are directly passed. So if this one is basically 1, so you do not have to pass it to the decompressor, directly you can apply in the circuit on that test. But for all this you require you have to use this Huffman decoding to find out the exact values like this and this. So what is the gain? So the gain is that your decompressor circuit inside the cut will be of smaller area. But what is the cost you are paying? For certain patterns which are rare in that manner will take a higher width, channel width, and but from the AT, so cost will rise, but not to worry that much, because that they are very rarely occurring patterns. This is the expression given for this compression ratio. So you can see that if you are using flat, so it will be n into the number of symbols, that whatever 4 bits are there, so 4 bits and 32 patterns were there, that is flat. And in this case, if you are using a Huffman coding, so 10 into 2, that means 10 patterns or there are bits, means 10 frequency is 10, so those patterns basically only require 2 bits. So 10 into 2. There are 9 patterns which will be also 9 frequency which will also be encoded into 2. So 7, these are where 2 bits. There were some 3 patterns which required 3. So if I do all this simple calculation, I will find that the efficiency is 1.71. That means that much less amount of channel width is required. Simple calculation that I apply that the compression is there. And flat, or if I just count the bit into frequency and I divide it, I get the compression ratio. So in this case the compression ratio will be slightly less, but again the hardware circuit used for decompression will be lower. Then I am going to take another, because there are so many examples I can go on, but I will just take one more before I switch to the linear circuits based scheme. So another is called the dictionary based scheme. So in dictionary based scheme, what is the basic idea? Take the advantage in the number of again commonly occurring sequence. But mostly the idea is similar, that basically if some of the bits which are having more frequency, you try to use them for lower number of bits encoding, and for which we are having higher number of which are more frequent, you embed using lower number of bits, and for higher ones, less frequency of occurrence, there you can use slightly more number of bits to encode. Basically this is what is the coding idea. Or another way, in the worst case, can be have very big width, compressive, equivalent for all. That I will try to see in the next scheme. But in most of the coding based scheme, that is the thing we try to follow, that based on frequency we will try to short it. But again, for most, there are some other coding scheme also, they will take it in a different manner. But mostly I am telling that this is what is the idea we take, based on frequency we do it. That is called frequency based coding, which is the most popular in case of this test compression techniques in case of circuits. But as I told you, there can be there can be other different ways of handling it. And basically in this lecture we are not going to elaborate in all the such schemes, because it is a huge in number. We are just going to give you the gist of idea of how compression is done using coding scheme, and you can, after doing this lecture, you can read any scheme, and as you have the motivation that why it is required, you can easily understand them. Next you are going to take a dictionary based. The idea is taking the advantage of commonly occurring sequence, same like this. Each symbol is treated as an entry in the dictionary, because like a symbol means, here we have, in the previous example we had made chunks of 444 and we made a symbol, it will be an entry in the dictionary. Each code word, then each symbol we are coding it, each word is treated as an index to the dictionary. That means there will be a dictionary where there will be all the symbols like S0, S1, S2. Symbol means basically your test patterns. And there is a code word. Each one of them will be encoded. Some values I will encode them. Now basically this encoding is actually the index to the dictionary. So if I want to apply S0, basically you will be applying this index. So this dictionary will be the on-chip circuitry which will take this index and it will generate the corresponding test pattern. Very simple. But this one will be of larger width, of course, and indexing will be a smaller, as we all know in the English dictionary, and we search by the index. So when we give the input, the output will be there. Again, here also we have to see how we can actually make this dictionary size smaller in hardware. Again, as I told you, just like the motivation from select and Huffman coding, here also people use it. 1 means it is encoded, available in the dictionary. 0 means it is not encoded, not available in the dictionary, you have to directly apply it. All these things are done to make the basically your dictionary size compatible, or sorry, dictionary size reasonable. So there are some kind of test patterns, as you can see. Let me zoom it for you. So this is your test patterns, and but here also we take care of compatibility, unlike the previous method. In case of Huffman, we generally do not think about the compatibility in that manner. You can also apply, there can be modified Huffman plus compatibility approaches, because you can make merger and all, but generally the two preliminary approaches we have discussed for Huffman, they do not think of compatibility as such. So what they do, basically you can see, in this case in dictionary method, so what we can do is we can use compatibility. Just look at this set. So you can find out that the vector some x's will be there, so there can be lot of compatibilities. Like for example, let us take the first two. So you can see 1x, 0x, 1, 1, x0, 1, 1, 1, this one. So very easily you can observe that test cube 1 and test cube 2, that these two test patterns are compatible. So I can write in this one, you can see these are the two compatible vectors. These are the two compatible, I make it compatible, and then I give the code word as 0, 0, 0, 0. That is the index to the dictionary. So and the flag bit is 1. That means basically they are compressed. So you have to, they are available in the dictionary. So if I give the input 0, 0, you have to generate the compatible test vector to this. So compatible here will be 1, 0, 1, 0, 1, x can be anything, 1, 1 0, 0, this 0 will come over as 0, 0 and 0. So basically if you look at it, this is the first test vector which is actually available over here, the compatible version. Now this will go, so you can find out that this one actually is compatible, the third one will be compatible with the sixth. If you can find out, you can just study, this one will be compatible with this, So again, so this will be going to the next index 0 1 0 1. This is the next index, and this is the vector which is not compatible. So I am putting with another index called 1 0, but all the LSBs or the flag bits are 1, which means that they are can be found in the dictionary. So this 0 0 is the first compatible vector, 0 1 1 0. So by this code word, these are the vectors. So if I put 0 0, so this pattern will be generated. If I give the input as 1 0, this, and 0 1 is this, 1 0 is this one. So of course, basically now your channel width for your AT is 2. So only 2 bits you will give, and the dictionary will be finding the index, and this one will be generated. So basically it is nothing but it's some kind of a combinational circuit you can design with input 0 0 1 0 1 1. Now I will come to the interesting story. And maybe I find out that this test vector is very rarely occurring, so I will put 0. So if such a test vector will be directly given as input. So in most of the cases you will be purchasing 2 ATE channels, but for only in a rare case you will be purchasing a longer set of ATE channels. So your job will be done. Very simple idea. Now question is that how can I design this circuit? So your input is 0 0 0 1 1 0, and outputs are this many. So very simple Karnaugh map you can optimize, 2 variable Karnaugh map. How many outputs will be there? 1 2 3 4 5 6 7 8 9 10 11 12. So 12 Karnaugh maps I have to solve, and I can get a digital circuit, and I will get this. Very simple. Problem, it is going to be a very large implementation. So if you go by a flat structure, as I have told in this case, you are going to land into problems, because your encoder, decoder, whatever circuit you put in your chip in terms of DFT, in the name of DFT, will be very large. So in the next gen circuit, they use linear decompression based scheme like LFSR or XOR based network. The interesting idea of such circuits is that you can do such operation, not always. Means I am not going into the theory of LFSRs or linear circuits. It's an extremely complex coding theory. Entire literature is available. If required, you can go through it. Here I will just give you the idea that there is some as I call you linear circuits, like linear feedback shift registers. Generally there are flip flops, there are feedbacks, and we have XOR gates in between. And this is a combinational circuit, slightly simpler version. You can see the inputs output will be only connected through a chain of series of XOR gates. They are actually called linear operations. When we will be representing in matrix terms, we will be doing in terms of AND. I will tell you this standard theory. So basically this is nothing but some circuit. How we are getting this circuit, I will tell you, but there is a lot of mathematics behind it, that how can we design such a circuit. But only thing you have to note that there are only XOR gates. And simple equation form is x0 equal to x3. So if you can see x3 and the output is O0. So this is simple, O0 is equal to x3. If you study O1, this output 1 is x2 or x3. So output 1, if you see, it will be this gate, and is nothing but x0 and x1. Simply if you just study this circuit, it's a very simple, you can find out that I can write this equation. But how the circuit is obtained, we will tell later. But the entire theory is very complicated. We will not go into that. Say some circuit is there, and somebody has told you the property that whatever we are discussing here, like some input is there, you can generate all the, like some circuit we can generate by normal Karnaugh map optimization, that some combinational circuit is there, input is there, required output will be generated. But that will be large, because it will have ANDs or NOT gates. But basically such kind of a linear structure is also have the same properties, but it cannot be always guaranteed, because in this case whatever input patterns and whatever output patterns you require, you can get a little circuit for that. But in such cases the input output is restricted. Like for all possible combinations, you may not be able to obtain such a circuit. But there exist lots of input output combinations, because there are a lot of excess. I will tell you what they are, then it will be more clear. So these are some bits, less number of 4 bits which the tester will give, and these are the outputs which is the input to the cut. This we know, this is your ATPG. This is your ATPG pattern. But we are using a less, as already we are trying to do. Here your number is also some 11 or 12, and you are using 2 bits to do it. Here I am having 4 bits as input, and output will be some 10 bits. So they are known values, means they are basically your ATPGs. That has to be applied to the circuit under test. But somehow we have to compress it using 4 bits or 5 bits or whatever. So generally there is a lot of mathematical theory in coding theory of linear networks, which tells you that if these values are known, and we know the number of number of bits required to do it, in this case I am restricting it to 4 or 5, whatever, this number is also fixed, and there is also all these variables are known. That means, and the idea is that, as I told you, there are a lot of excess, don't care. So then it can tell you that whether such a thing can be implemented or not. Better to take it, and when I will take an example, it will be clear. But the question here is that some values I know, there will be a lot of don't cares. That is what is the only boon I am having. Then can I design a very simple linear circuit by only XOR gates such that I can have a smaller width values, so that if I keep on applying it, all the known values can be generated, and this should not be as large as a combinational circuit. That is the question. So can a circuit be generated like this? The idea is yes. For many of the cases it can be generated, because there are a lot of don't cares here, but it is not a general case. Generally you may not be able to do it. It may be possible by 4, it has to be increased to 5, to 6. And of course, if you have 10 lines here, if you have 10 lines here, of course it is a direct mapping solution. Can I do it by 9? Possible. 8. So more you reduce, and of course you have to be very, very careful that basically this circuit is a linear circuit. You cannot put lot of complications over here. So from 10 is just direct mapping, 9, 8, 7, 6, 5, 4, you can keep on going it. But at what position? Because more less numbers here is more important. But it is not always possible to go beyond a certain limit to generate it. So those, it's not possible to generate this, you will not have such a simple circuit for that. But that theory is extremely complex, I am not going into it. But just take the idea right now that for most of the cases it is possible that somehow I can get a sufficiently good number which is much less than the number of output bits, and still I can solve it. So if you have these equations, just you can map it. I can simply represent it is in a matrix form. So the matrix form is something like, I will zoom it for you, it's very straightforward operation. Like in this case, this whole matrix I am representing, so 9 will be the 10 will be the output. So here we will have 10, I think 1, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is the number of columns, number of rows is 4 inputs. So 1, 2, 3, 4. So x0, x1, x2, x3 are the inputs and 10 are the outputs. So row by column matrix we have, if you see 0, 0, 0, 1. So it is x0 is 0, x1 equal to 0, x2 is also equal to 0, x3 equal to 1. So x3 is equal to O0. So that is what is the first equation. Similarly you can do it. So whatever is XOR over here is generally taken as AND in the matrix. This is a simple matrix representation. Now I am directly coming to an example. How I have got these patterns, you will not think about it. Say this is the pattern set I am getting. Again I am saying that is the represented in a vertical manner. So first pattern is 0x, something is there. The second pattern is 2, x, 1, some values are there. Observing that I have 4 deterministic values only. So in this case 1, 2, 3 and 4. Here also 1, 2, 3, 4. So in most of on all the channels, if you see all the test patterns you see, there are only 4 deterministic values, all are don't cares. So that actually motivated me that can I have 1, 2, 3, 4 bit inputs which I feed, and there will be a decompression network. Of course, the decompression network has to be very simple. If I make it extremely complex, then you can have any mapping. You take this as input and you want to generate this as output. You take the second as input, you generate this as output. So I can easily solve some Karnaugh map optimization and I can have a general digital circuit for that, combination circuit. But that I don't want to do it. I only want to do it by linear operations. So that this decompression circuit is less. So only by XOR gate, such structure. So is it possible? So the theory says that basically you are seeing that we have only 4 ones here. So let me just try to keep this number as 4. Is it possible by 3 inputs? Maybe, but I do not know, because the theory exists. Whether it will, all of those theory will prove you that whether it is possible with 3 or not. Can I do it by 2? More difficult. For most of the cases it will be no. But can I do it with 8 inputs? Means this channel with 8, it will be a more easier problem to solve. So that actually a lot of theory exists to find out whether it is possible or not. So for the time being, I am just giving the theory. So what we are doing, we are finding out that for every case, the number of ones is, deterministic values are 1. So I may hope that this will be okay. So then what? Then basically what I am trying to do, let me just take this 4th vector. So the 4th vector, if you look at is x, x, 1. So O2 is very important, O3 is very important, O7 is very important, and O9 is very important. So just if you look at it, we are just taking the deterministic values. So O2, O3, O1 and O0. These are the most important ones. So I will have the equation O3, O2, O3, O7, O9, and x0, x1, x2, x3 is fine. But now how I am getting this smaller vector? Because this O3, O2, 3, 7, 9. So O2, 3, 7, 9 are the most important one. So 2, 0, 1, 2. So this 2, then 3 and some 7 and 9. So these rows I will select and I will have a truncated matrix. So this was the truncated value, very simple. So now basically you have to, this is given to you. So this is the reduced vector, reduced matrix which I have got from there. These are the inputs and these outputs, these are, no, this you have already found out as O2 is something like 1 1 1 0. This is 1 1 1 0. So this is 1 1 1 0. Now you have to find out the value of x's. So you can go for a standard Gaussian elimination based equation solver, and that one will tell you that what are the values of these variables. So it will tell that x0 is equal to 0 0 0 1. So it will put it as 0 0 0 1. Now you have to solve it for all the levels 1 2 3 4 5 6. You have to solve all the values. Now this one is for 1, if you solve it you will get this value and so forth. Now it is very interesting that you can, using this circuit, basically if you apply these patterns, you are going to, by these 4 patterns you will apply this, you are going to get this pattern. But the x's can be 0 and 1, that I don't know, but still all the meaningful values you will get by applying this. So this decompressor circuit is now not a full combinational circuit, but it's a rather a simple linear circuit, and you are trying to get the effect. So that is the idea of linear decompression based scheme, or by using an LFSR also a sequential circuit to do the same thing. The idea is that we will be using less number of bits and we will be going to generate a higher bit size. But the circuit I will be not using as a full combinational blow up, I will be using linear operations, and in fact it is possible to do, but this theory exists that what is the input size, what is the number of output size, what is the number of x's required, and what are the don't cares required to do it. For it is possible. For all combinations it may not be possible. So of course, as I told you, it's not a very simple problem, because it may be possible if I have some maybe 1 x here and 1 1 here. Can the ATPG algorithm, ATP test pattern be changed like that? Can I test some faults by keeping a x over here and a 1 over here? So then again it's a feedback to the ATPG algorithm. So it happens in a queued fashion. So it tries to find out, okay, I will only have 3 channels and this is the pattern required. I find out that there does not exist any linear circuit to do that. So either I can use it to 4, or I can somehow modify the test pattern so that it becomes compatible. So there are a lot of iterative based heuristic algorithms to solve the problem. Now slight more theory I will tell you that when it is possible. So the technique necessitates that the unknown xi is to find out the xi's given the oi's. That means you know these values, and you have to find out the value of xi. But number of oi's and number of xi's are fixed. So if oi is an unspecified bit, you need not solve anything. That is what I have seen. That is only 2, 3, x7. For whatever you are considering, you have to find Gaussian elimination for whatever is specified. For particular values of oi's, the equation can be solved as long as the number of specified values does not exceed the rank of the matrix. So what is the rank of the matrix? This, as I told, is a more theoretical this one. So basically in broad sense, rank of a matrix means how many independent columns relations you can form. So in this basically example, this is a full rank matrix. That means none of the columns basically in this matrix, none of the columns are dependent of any other. So if you have but how the column has been generated? The column has been generated based on this circuit. So there is a plain theory saying that for particular values of OI, the equations can be solved as long as the number of specified values, that is specified values means which are non-excess in OI, do not exceed the rank of the matrix. Even when the number of specified values exceeds the rank of the matrix, a solution may exist depending on the value specified. Then we do not guarantee. So in this case, if you see, we have taken only 4 as specified bits. And also if you see that the 4, as I told, the full rank matrix, so the rank will be, there will be all columns are independent. So here I safely can put 4 values which are specified in each of the patterns. So in this case I am always able to get a solution. Therefore that means what? In this is a full rank matrix, then I have only 4 over here. So basically I will be always able to find out a solution which will generate this. But this is not very optimized. So you can even increase the number of specified values. But still, whether can I get a solution with 4 inputs, that may not be guaranteed. That will depend on the outputs, because in that case the number of specified values will be more than the rank of the matrix. If in this example we consider only the case where the number of specified bits is less than or equal to n and the result matrix has full rank. So basically we have considered specified to be n to be 4 only, because only specified bits is 4 and the rank matrix is full. So in this case it was satisfiable. But exploration of the remaining cases is a complex problem and we are not dealing with it. That is whether if you have 5 values specified and the matrix is not a full rank matrix, then whether we can find out such a linear circuit or not. So there are a lot of theories available for this. Extreme, it's a bit complicated subject, but you can look over it. But what I have tried to show you is that basically in linear compression based scheme, if we have less number of specified bits and we have a reasonably large rank matrix, then you can have a simple translation scheme, and this decompression network will be very, very small, involving only XOR gates, or in some of the cases flops and XOR gates, not full blown up. So basically this is the encoding efficiency, and lot of linear decompressors can be there, fixed length, variable length, sequential, non-sequential, so many are there. So basically these are two main techniques which are used for actually encoding or compressing your inputs. A third one, as I told you, will be about your scan chains or broadcast scan, which I will cover in the next lecture. Now before we complete, quickly we will look at what about the output size, because the output also you cannot take the full one and put it in the memory, that is also not possible. So the expected output golden response of the cut cannot be stored explicitly. So basically there are a lot of ways to compact. This is not a compression, it's a compaction. So there will be the lossy compaction, so sometimes there will be aliasing. I am taking two most important ones. One is counting the number of ones and one is the transitions, how many changes are there. There are several other techniques like LFSR, signature registers, etc. for this compaction, but in this course I will be taking the most simplest ones. So it is a very simple example. This is a circuit, maybe the patterns I am applying is 1 1 0, then I am applying 0 0 1 and so forth. There are 1 2 3 4 5 6 7 test patterns, because here I am applying showing in a vertical manner. So this patterns is there, and this is the output, the number of ones is a 1. So in this case there will be a counter which will count the number of 1 and it will generate the answer as a 1, which will be fed to the ATE. Now say there is a stacked fault in the output at this line. So the number of ones, so if you do an AND, we will find that the output is this. The output is this. So the number of ones will be 2. So you will just send the count to the ATE memory, you will find out that there is a mismatch in the number of ones. So this circuit is having a fault. So instead of sending 7 bits, we can just send 2 bits to encode the number of ones, because this 7 is the number of test patterns. So maximum 7. So 3 bits will be required at the output. So you can count how many numbers of ones and the fault will be detected. But so in this case, whatever I told you is written in this slide, you can do it, but it is not always the case. Let us take a slightly modified example. Same thing. How many patterns I am giving? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7. Again same patterns are there. This is the circuit. If you do it, this is the normal circuit. The output, the number of ones is 2. Now I take a stacked one over here. The output pattern is this one. This pattern and this pattern are definitely different. So very easily you can find out the stacked fault if you are feeding this 7 bit as the output without compaction. But now I am compacting it by the number of ones. So here also 2 ones, here also 2 ones. The positions are different, but I am not keeping the positions in mind. I am just taking the number. So in this case, the fault is there, still you will not be able to detect, which is called a aliasing. So it's a lossy compression. So you are having an aliasing effect. So as I told you, counting number of ones is a very rudimentary approach. There are a lot of advances are there, but I am just giving the idea so that you can refer to any of the techniques, because all these things are based on coding theory. Coding theory, the theory itself is so well developed that you should have a full course on coding theory to get into ideas on all these things. But I am telling you from this viewpoint of the circuits. So once you have the more idea on coding theory, you can easily map it to the case of VLSI. So this is actually called number of 1 compensation given aliasing. So in this case the fault is not detected. Another technique which is called we apply is called basically your transition. Normal circuit, same patterns I am applying. So you can see 0 0 0 1. So one jump from 0 to 1 and one jump from 1 to 0. So there are 2 types of transitions. So the transition count equal to 2. Now I am having again the same stacked one fault. So here also the transition count is 1 1 0. So 1 transition and 2 transition. So here the transition is 2, but again the fault is not detected. So another technique I have applied, which I am showing, is basically transition by compaction. You just find out how many times it is changing from 0 to 1 and 1 to 0. So there is 2 jumps over here and here is also 2 jumps. But you look, the patterns are different. So if you are using the counting one sequence, the fault can be detected. But when you are using a transition count, this fault is getting aliased. But for other cases, it may be the vice versa case. Like the same circuit I am taking, the second example, same inputs, the pattern is something like this is the output, the transition count is 2. I am changing the circuit. So in this case, I am again taking a stacked one fault. Now the pattern is something like this. Patterns are of course different, very easily you can detect it, but here also the transition count is now changing. So in this case you see 1 transition, 2 transition and 3 transition. So here the transition count is 3. So in the second example, transition count based compaction can detect your fault, but not the counting number of ones, and which was reversed in the other example. So in fact, what I mean to say here was basically when you get the output, we do not compress it. Rather what we go is we go for compaction. And there are a lot of compaction techniques. Two very preliminary I have given you an idea, but for many of the cases, just like we are very successful in compression, for many of them, most of the cases aliasing do not happen, or very rare aliasing happens. So with slight modification in technique, like if you are using LFSR based compaction or some other methods of compaction, the aliasing effects are very rare, very less, and we can actually have a very small bit width representation of the output to get a very good fault coverage. But here I have given you two very stray examples to show the strength of each of the compaction scheme, that it may work for one circuit and it may not work for another. But for a general case, for most of the good compaction techniques, this phenomena is less. So with this we come to the end of this lecture. In this lecture we have tried to show that given a circuit and given some ATPGs, how can we mainly compact by compacting the width. So 10 bit is the input pattern to the card, how can we replace by 4 bits or 2 bits so that we can save on the ATE channels. And secondly, also the output is also having some width, so how can we compact the width by compaction so that we can have more efficient in terms of complexity, so that we can have even for very large circuits, still we can optimize the test patterns so that we can have a reasonable cost in the ATE. I should tell that this is a solution we are getting by paying some cost in terms of coverage and also some extra area overhead in the circuit for compression and decompression. But still, if you have a very large circuit, there is no way you have to go by this, otherwise your test cost will be so high that you will not make a profit in the market. So basically, even with slight trade off in fault coverage guarantee, you can go for this compaction. So with this we close now, and from tomorrow's lecture we will see how DFT circuits can be optimized mainly in terms of scan chain to have better quality, or how we can whatever ATPG compaction we have done, how it can be again helped by the is the scan chains, how such optimization can be done taking in mind the scan chain structure. Thank you.